Hello everyone, welcome back. So out of the problems that we will be solving today, the first problem is based on rotational motion. So in this question, we basically have a pencil of mass m and length L, and it's placed vertically on a table with its pointed end downwards as shown in the figure. It is then released and it tumbles over. If there is sufficient friction to avoid slipping, then at what angle from the vertical, the normal force exerted by the pencil becomes 4 by 9 mg. So the problem statement is quite straightforward. So we have to find the angle theta for which the normal reaction from the ground becomes this value. Okay, now let's check out the solution. Okay guys, so let's say the current angular position of the pencil with the vertical is theta. So in this current situation, it will have some angular acceleration, right? And it will also have some angular velocity because it has been rotating for a while, right? Now again, the bottommost point is given to not slip. What that means is the entire pencil is rotating about this horizontal axis passing through the bottommost point. Okay, so or basically this is the instantaneous axis of rotation. So let's try to determine the acceleration of the center of mass. So the center of mass is again moving in a circle of radius L by 2. So it will have two components of acceleration. One is the tangential acceleration and another is the normal acceleration, which is towards the center of the circular motion. Okay, so the centripetal acceleration is going to be omega square L by 2 towards the tip of the pencil, and the normal acceleration will be simply L by 2 times alpha, and it is perpendicular to the radius vector. So this is the net acceleration of the center of mass. So now the forces that are acting on the pencil is first the normal force from the ground, then we have the mg acting at the center, and we also have the friction force acting. So let's just assume it's acting to the right. So first, let's write down the conservation of energy equation. So initially the center of mass was at a height of L by 2 from the ground, and now it's at a height of L by 2 cos theta. So which means the drop in potential energy is mg L by 2 times 1 minus cos theta, and this would be equal to the change in kinetic energy of the pencil. We know that this is the instantaneous axis of rotation, so the kinetic energy is going to be half. So this pencil, we can model it like a uniform rod, right? So its moment of inertia about its tip is ml square by 3 multiplied by omega squared, and from here we get this particular value for omega. Okay, so now we need to figure out alpha. So for that we'll use tau equals I alpha about the instantaneous axis of rotation. So about this particular point, there won't be any contributions to torque due to normal and friction. So the only contribution will be from mg, and the moment arm is going to be L by 2 sine theta. So the torque due to mg is mg L by 2 sine theta, and this would be equal to I alpha. So from here we get alpha as 3g by 2L sine theta. Okay, so now again we are only interested in the normal forces. So we'll now write sigma Fy equal to m times AYCM. So we're going to write down force balance in the vertical direction. Okay, so from the diagram we can see that the net acceleration is in the downward direction. So we can say the net downward force, which is mg minus normal, equals mass times the acceleration. So this angle over here is also theta. So the net downward acceleration will be omega square L by 2 and the cos component of it, and L alpha by 2 and the sine component of it. Okay, so now what we are going to do is substitute omega and alpha into this equation, and let's see what we get. So once you substitute and solve, you get this expression for the normal reaction, and this if you observe is a perfect square. So this is 3 by 2 cos theta minus half the whole squared. Now we wanted the normal reaction to be 4 by 9 mg. So now we can take the square root on both sides. So this becomes 2 by 3. The RHS becomes 3 by 2 cos theta minus half. So after solving, cos theta comes out to be 7 by 9. And this implies that theta is cos inverse of 7 by 9. And that would be option C. So now let's move on to the next question. Okay guys, so in this question we have a cylindrical body that is floating on a liquid surface. So the line AB, which is this line over here, it passes through the diameter of this circle basically, and we have to assume the liquid and the material of the body makes a non-wetting combination with a contact angle of 143 degree at the circumference of the cylinder passing through the line AB. Okay, so at this particular point over here, the liquid surface makes an angle of 143 degree with the vertical. The line AB is at a depth h below the horizontal flat part of resurface. So if we draw the continuation of this surface, this liquid surface will be flat, and closer to the sphere it depresses by a bit, and the exact height is given to be h. Okay, so we have to neglect the effects of surface tension at the flat ends of the cylinder, and that basically includes the front and the back of the cylinder. So we have to ignore the surface tension forces over there, and some values are given. We have to find out the value of height h and the density of the cylinder. All right, so let's start with the solution. Okay guys, so this is the situation. So the tangent to the fluid surface at this particular point was given to make an angle of 143 with the vertical. So basically with the horizontal, it will make an angle of 53 degrees. So first, as we have to figure out the value of h, we'll take the FBD of this portion of the fluid. So in 3D, this part looks something like this, right, from the side view. So what we're going to do is we're going to chop this particular part of the fluid surface, which means the part on the right will be pulled towards the left by surface tension forces, right? Let's draw its FBD over here. If we look at this fluid layer from an angle, it will look something like this. So we actually sliced this fluid layer along this plane, right? So the fluid on the left would pull on this layer towards the left. So we have to mark surface tension forces like this. So this is the force that the fluid layer on the left will exert on this line, right? So let's take an inward length of L. So the surface tension force at this on this layer is going to be T into L, right? Similarly, on this layer into the plane, the surface tension force will be first tangential to the line, and the tangent makes an angle of 53 with the horizontal. So this angle will be 53 degrees, okay? And this also will be T into L because we are taking the same L length into the plane. So in 3D, this is the length that we're talking about. So this will also be length L, okay? So now the thing is, guys, we only have to care about the horizontal forces. So let's try to write down the pressure forces first. So the first point we have to discuss here is that we don't have to consider the atmospheric pressure forces when we are figuring out the net force. And the reason for that is pretty simple. So P0 is actually acting everywhere. So, and it's a uniform pressure, right? Whenever we want to figure out the force due to a uniform pressure, we use the idea of projected area. So let's take this surface for example. P0 is acting everywhere, right? So if I want the horizontal force acting on this layer, then I'll take the projected area in the vertical plane, which is actually this area, right? So the horizontal force acting on this layer will be P0 times the area of this vertical plane, which let's just say it is A. But the same P0 A will act from the left as well. So they both cancel. Similarly, the vertical force will be P0 times the projected area in the horizontal plane, and that area is going to be this area itself. So let's call the area as A dash. So from on the top layer, it will be P0 A dash, but on the bottom layer also there is a force of P0 A dash. So the net force due to atmospheric pressure, it cancels out. When you sum all the contributions, that just adds up to 0. So we don't really have to include it. So instead we can work with gauge pressures. Pressure everywhere outside is P0, right? And we know that as it is in hydrostatic condition, the pressure at a height h below the surface is P0 plus h rho g, and it's going to remain the same everywhere along the horizontal. So everywhere along this red line, the pressure is actually P0 plus h rho g, okay? But on this vertical layer, and it's going to linearly increase. So if I want to show it in a triangular diagram, pressure is going to look something like this. So the gauge pressure is 0 at the free surface, and it's going to linearly increase with depth, and reaching its maximum value of rho gh at the bottommost point. So whenever we have a surface that is submerged under water, guys, the way we find out the net force on this surface is we figure out the pressure at the centroid of the surface and we multiply it with the area of the surface. And you can find this result out in some of my Pathfinder fluid videos. So again, the centroid of this vertical length is exactly at a distance of h by 2, right? So let's write down the formula first. So the force acting on that vertical line is the pressure at the centroid multiplied by the area of the surface. So the pressure at the centroid is simply rho g h by 2, and the area of the surface, this is a rectangular surface whose vertical length is h, and so the area of the surface is going to be h into L. So this force comes out to be rho g h squared L divided by 2. So now I'm going to get rid of this diagram and I'll directly show it over here. So the net force acting on the surface is F. Okay, and I'm not writing down the force acting at the bottom surface because we only want the horizontal force, guys. Okay, so now we can write sigma fx equal to 0 for this fluid element over here. So we can say F plus TL cos 53 equals T into L. So once you do the force balance and solve for the value of H, you get the answer of H as 1 mm. Okay. So the next question that we have to discuss is the density of the material. And for that, we obviously have to do force balance for the cylinder. Okay guys, so now for the cylinder, first we have the weight of the cylinder acting. As half of this cylinder is submerged under water, there will be a buoyant force acting, and also we have the surface tension forces. So these are the forces that are acting on the cylinder. But in this situation, there is a small catch here. If you write the buoyant force as the submerged volume, which is V by 2, right? Half the cylinder is submerged underwater. So submerged volume into the density of liquid into G. If you write this as the buoyant force, you actually won't get the answer. The reason for that is because the surface of the fluid actually depresses a bit, right? From our previous discussion, we discussed that the pressure everywhere on this layer is P naught plus rho GH, right? Similarly, the pressure everywhere in this layer is going to be P naught plus rho GH. But just outside, the pressure is just P naught, right? So if you observe something, if I go from just outside to just inside, there is a jump discontinuity in pressure. So let's call the point just outside as 1 and the point just inside as 2. So the pressure at point 1 is P naught and the pressure at point 2 is P naught plus rho GH. Let's take our standard situation of, a cylinder that is half submerged underwater. In this case, we write the buoyant force as V by 2 rho G. And the difference between these two cases is that, guys, if I take similar points 1 and 2, the pressure is almost going to be identical, right? There is no jump discontinuity here. The pressure will slowly increase as we go deeper and deeper into the fluid, but there is no sudden jump in pressure. So clearly in this case, the buoyant force will be greater than the buoyant force in this case, because here the individual pressures acting is less in comparison to this case. So we have to think about this in a different way. So we have to determine what the actual buoyant force is. So buoyant force actually arises because of the reason that as we go deeper and deeper into the fluid, the pressure rises. So as you can see, there is a non-zero upward resultant of the forces, and that's what is creating the buoyant force, right? So let's just mark down the pressure forces first. The point 1 that we discussed here, we don't have to include the P naught when we are figuring out the net force. So here also we are going to forget about P naught because everywhere at each particular point on the cylinder, the atmospheric pressure is acting. So to the net force, it won't contribute anything. So the gauge pressure at each point that lies outside the fluid is going to be 0. Why? Because it's exposed to the atmosphere, right? So everywhere outside the gauge pressure is 0. So now once we go inside the fluid, there is a sudden increase in pressure of rho GH. And as we go deeper, it increases by a bit and it keeps on increasing till we reach the bottom of the fluid. And at the bottom, again, it is at the maximum value, right? So, and you can also figure it out. So the bottom of the cylinder is at a depth of H plus R from the free surface. So the pressure here will be rho G H plus R, the gauge pressure. So guys, so the lift produced on this cylinder is actually because of the resultant of these pressure forces, and that is what we call as the buoyant force. So let's say the resultant of all these is actually F1. So our goal is to find out F1. Now there are two ways of finding out F1. I mean, two ways of thinking about it. One way is we have to think about a situation where the gauge pressure profile is something like this. So basically we want the gauge pressure at this point to be rho GH. So if we take our standard case where there is no curvature in the surface, and if I dip this cylinder in such that its center is at a depth of H, you guys can see that at this particular point the gauge pressure is now rho GH. So the pressure profile on the lower half is now exactly identical to this case, right? There is no difference between these two. The only issue is that now on the top surface also there will be some gauge pressures. So we can actually do something about it. So if I draw the diameter, right? And if I chop off the upper surface, so now we don't have that problem, right? Of, dealing with these pressure forces. The pressure below still remains the same. The pressure below is still identical to this case. Now in this case, we have to deal with the pressure on this surface, on the flat surface. But that is very easy to write, right? So the gauge pressure at the flat surface is simply rho GH, right? Because each point on the flat surface is at a constant depth of H from the free surface. So we can say the force acting on the free surface is nothing but the pressure, which is rho gh, and it's same everywhere, times the area. So again, this is going to be a rectangle, right? So its length is 2r and its breadth is going to be the length of the cylinder, which let's take it as L. So the area of that part is going to be 2r into L. So the other force will be the fluid pressure acting on the curved surface of the cylinder, right? But this is exactly identical to our original question. So the resultant, we actually took it as F1, right? So let's just mark it as F1. So now we can say that F1 minus rho gh times 2rl is what is creating the lift on this semi-cylinder, right? So and that lift is what we call as buoyancy. So this is actually equal to the buoyant force in this particular case. And in this case, we know the answer for the buoyancy, right? It's the submerged volume, which is actually pi r square L by 2. Only half the cylinder is present, times the density of the fluid times G. So from here, we can figure out, we see that the buoyant force comes out to be pi r square L by 2 rho G plus rho GH times 2RL. And from here we can easily see that the buoyant force comes out to be greater than the weight of the fluid displaced in this particular case. This is one way of thinking about it. One more way to think about it is that the original problem, if I make the gauge pressure here 0, and then I make the pressure to increase with depth. In this case, the buoyant force comes out to be the submerged volume density of the fluid into G. But the difference between this case and this case is that to each pressure term, a rho gh is added. So the pressure everywhere increases by an amount of rho gh. So it's kind of like inside this fluid, somehow everywhere the pressure increased by an amount of rho gh. Now we can use the result for the uniform pressure case. Okay, so and now we can forget about the original lines, and we can assume that a uniform pressure of rho gh is acting everywhere. Okay, so this is rho gh. So this is going to be rho gh. So if a uniform pressure of rho gh acts everywhere on the cylinder, then the resulting upward force we can figure out using projected area, right? So the projected area of this semi-cylinder is going to be again a rectangle, which is 2r and times L. So that force is going to be the uniform pressure rho gh times the projected area. And as you can see, these two are exactly the same. So now as we have the buoyant force, now we can do a force balance on the cylinder. So if I draw the FBD of the cylinder, okay, so on the cylinder, surface tension force will act along these lines, and it makes an angle of 53 degrees with the horizontal. So the net upward force due to surface tension will be TL, where L is the length of the cylinder, into sine 53, and 2 times of it because it is acting along both sides of the cylinder. So this is the upward surface tension force. That if we add the buoyant force, this should be equal to the weight of the cylinder, which is pi r square L volume density of the object into G. And once you substitute all the values in, you'll get the answer for the density of the cylinder as 3909.82 kg per meter cube. Okay, so that was this question. So now let's move on to the last question. So yesterday IIT Kanpur actually uploaded a sample paper, for JEE 2024, and this question was taken from that. And this is basically INPHO 2019 PYQ. So let's read the problem statement. So we have a setup in which 2 long parallel metal rails of negligible resistance placed horizontally apart with a distance of d. A horizontal metal rod of mass capital M and resistance R is placed perpendicularly on the rails at one of the ends. So this rod has a resistance of R. There is a uniform magnetic field directed perpendicularly to the plane of the rod arrangement. So let one end of the rail track is connected to the key and a capacitor of capacitance C charged to a voltage of V0. So the capacitor is already charged to a potential of V0. Okay. At time t equal to 0, the key is closed. So we have to neglect friction. So there is no friction in the rails. Neglecting self-inductance, in other words, just means that there won't be any L di by dt back EMF due to the changing current. So we have to figure out how the charge Q is changing and the final velocity of the rod. In option B, they are saying at time t equal to 0, the charge Q0 is just CV0. This is like really obvious, so I don't know why this is an option. So that was pretty direct. So let's say at some general time, the charge on the negative plate is minus Q, positive plate it is plus Q, and some current I is flowing on the circuit. So the current I will be in the downward direction as seen from above for our conducting rod. Okay, so now the magnetic field is pointing into the plane. So now we know that whenever we have a current carrying wire and it is placed in a magnetic field, it experiences force of integral I dl cross B, right? And the direction of the force you can figure out using I cross B. If you do I cross B, you'll get the direction to be towards the right. Here, as the direction is I, is the same for all dl elements. We can just directly write the force as ILB. Okay, L is the length of the rod. So the ILB force is the only force acting on the rod in the horizontal plane. So we can first write down that ILB, which is the net force, equals the mass times acceleration of the rod. Okay, so this is equation number 1. Now for second equation, we can write down the KVL equation for this loop. So as we go from the negative to the positive plate of the capacitor, there is a potential rise of Q by C, and capital Q is the charge on the capacitor at any general time, guys. Okay, now the conducting rod has a resistance of capital R, so the potential drop across the resistance is going to be I times R. Now as the rod is moving perpendicularly to the magnetic field, there will be an induced EMF due to the magnetic field, right? And that induced EMF is simply integral of V cross B dot dl. And that integral for this case, most of you may be familiar with. It just comes out as VBL. And the polarity of the induced EMF you can judge by figuring out the force on a positive charge. So let's say the velocity of the rod is V in the rightward direction. So if you do V cross B, the direction comes out to be in the upward direction. So the positive polarity will face the upward direction. So you can consider this as a battery, something like this, and the induced EMF is actually BVL. So now as we are writing KVL in the clockwise sense, there is a potential drop of BVL. So we have to write minus BVL, and it would be equal to 0. Okay, so we can send IR and BVL to the other side. So, and let's say this is equation number 2. These are the two equations that we have at hand. So let's try to figure out the charge first. So there is an important thing that we need to understand here, guys. So the current I, in terms of magnitude, it is simply dq by dt. Right, so if a charge of dq flows from the positive plate of the capacitor in dt time, then the current is going to be dq by dt. But the thing is, guys, if a charge of plus dq leaves the capacitor plate, the magnitude of charge on the capacitor plate actually decreases, right? So dq by dt is actually negative. So the actual value of dq by dt is minus I. So you have to put this negative sign, and this is saying that the charge on the positive plate of the capacitor is decreasing. Okay, so keeping that in mind, when we look at these two equations, we can see that there is a dv by dt term here and there is a v term here. So let's try to differentiate equation number 2. So on the left side, we will have dq by dt, which I am going to write it as q dot divided by c, and this would be equal to, again guys, as my intention is to find out q, I'm going to replace I with minus q dot. The derivative of that is minus q double dot. So here there will be a minus q double dot term times r. Okay, and plus b, dv by dt is v dot times L. So now what I'm going to do is I'm going to substitute the value of dv by dt and put it over here, which comes out to be this particular value. Again, I'm going to replace I with minus q dot. I end up with this differential equation. Okay, so this entire thing in the bracket is actually a constant. So I'm going to term it as k for now, and I'm going to take q dot to the other side. So this becomes q double dot divided by q dot. The right side becomes minus k. So now what I'm going to do is I'm going to integrate on both sides with respect to time. Now again, guys, both of these are functions of time. If I put q dot as a function of time as some u, I can say q double dot dt is du. This is like the integral of 1 by u du. So this just comes out as ln mod of q dot of t. The right side becomes minus kt. Okay, so now let's put the limits. So at time t equal to 0, the value of q dot. So, and q dot is just the current, right? So we want to figure out the value of the current at time t equal to 0. Clearly there won't be any motional EMF because the motion hasn't started yet, right? It doesn't have any velocity. The rod doesn't have any velocity. So the capacitance is going to act like a voltage source of voltage V0, and the current in the circuit is going to be V0 divided by R. And that you can see from here as well, from this equation as well. So BVL will be 0. Q is going to be CV0 at time t equal to 0. So current is going to be V0 divided by R. But you have to keep in mind one thing. It's not the current, it's Q dot. And if you guys remember, Q dot was equal to minus I, right? So you have to put a negative minus of V0 by R here. And at any general time t, let's say it is Q dot. The charge is a function of time as minus V0 by R e to the power minus kt. Okay, so this is the value of the current in the circuit. So now if you look at option A is clearly wrong. But even in terms of dimensions, it is wrong. So yeah. So now we are more interested in finding the final velocity of the rod. So for that, we'll go back to our velocity differential equation, which was this particular differential equation. So we know the value of I, right? I is minus q dot. So minus q dot will be v naught by r e to the power minus kt times L into B equals m dv by dt. So now we are going to just differentiate this. So this will be b v naught L divided by mr times e to the power minus kt dt be equal to dv. So at time t equal to 0, the velocity was 0. So let's figure out the velocity function with time. So the velocity function comes out to be this particular value. So this plot looks something like this. So it attains a steady state value after t tending to infinity. Okay, so after a very long time, which is what they asked in the question, v t tending to infinity, final speed comes out to be b v naught L divided by m r k. Once you substitute the value of k, you'll get this as the final terminal speed attained by the rod. And this actually matches with option C. So the answer to this question is option B and option C. Okay, so that was it for this video, guys. If you enjoyed the video, please do like, share and subscribe. And that's it. Thanks for watching.